The purpose of this video is to look at two different heat capacity examples. We're going to take a look at a situation where we have a substance that is changing its temperature and not its phase, and we want to find out how much energy was absorbed or released in order for that temperature change to occur. So when we read the question, it tells us that the temperature of 20 grams of water is increased. So the temperature is changing from 22 degrees Celsius to 72 degrees Celsius. If we're observing a change in temperature, that must mean we're also observing a change in thermal energy. Observing a change in thermal energy, it's most helpful for us to first actually create our temperature versus time graph. So for water, we're going to have our freezing temperature on the graph at 0 degrees Celsius and our boiling temperature of water at 100 degrees Celsius. And we can see that our water is increasing from 22 degrees Celsius up to 72 degrees Celsius. 22 to 72. So we're going from somewhere around room temperature up to a pretty high temperature. That's not 72 degrees Fahrenheit, that's 72 degrees Celsius. Much hotter than a nice sunny day. So to correctly identify what's happening in our math, we want to create our LOL diagram. We know based on our graph that in our LOL diagram, we're going to have a change in thermal energy because we had a change in temperature. So we're going from room temperature, which we represent as about 2 bars of energy, from 2 bars at room temperature up to hot at either 4 or 3 bars. Whatever you do, we want to make sure we show an increase in thermal energy because we're increasing the temperature. Our substance is going to be water between those temperature ranges, liquid water, and we represent liquid water as 2 bars of phase energy. And we're not boiling any of this away. We're not melting it or freezing it. We are going to maintain the same amount of phase energy because we start a liquid and we end a liquid. And as always, we are going to include about 1 bar of energy for chemical energy. We're not observing a change in that. Our system is the water that's being heated, and we're heating it from 22 to 72, so heat energy is going in. The type of heat energy that's going in is thermal. If it is thermal energy that is changing, we need to use the equation Q equals M times C times delta T, because this problem is actually going to account for that change in temperature. And we're going to use our C value, this new idea of our heat capacity of water, which represents the amount of energy needed to increase the temperature of 1 gram of that substance by 1 degree Celsius. So mathematically, what do we know? We know the mass of the substance is 20 grams. We know that the specific heat of liquid water, we know it's liquid from our LOL diagram and from the question, is 4.18 joules per gram degree Celsius. And we know the change in temperature. We always want to do T final minus T initial. So T final is 72 degrees Celsius minus 22 degrees Celsius. And since we know all of those things, and we can go back in our question and read that we're calculating energy absorbed or released, so we must be solving for Q. At this point now, we're just going to multiply all of this together. It might help you to simplify this before you multiply all of the things together in case you are unsure about your order of operations. 72 minus 22 is 50. So 20 times 4.18 times 50, our energy absorbed or released is 4,180 joules. Now, is this energy absorbed or released? Well, from our LOL diagram, we can see that heat is being absorbed by the substance. It's going in. So there's our first example. In our second example, we have 3.5 kilogram sample of steam, water vapor, at 200 degrees Celsius, which is going to release 641 kilojoules of energy. What will be the final temperature of the sample? So the sample itself releasing energy. We know this from the question. And based on this information, I'm going to create my LOL diagram first. With our thermal energy, it's starting at 200 degrees Celsius, which I'm going to call pretty hot. And it's telling us that heat is being released, and it's showing us that there's going to be a temperature change of the sample. So we don't know exactly how much temperature change we're going to have, but we know it's going to be less. It's also assuming that we are not having a change in phase. There's no description of condensation of that water vapor. So we can assume that our phase energy starts at 4 and ends at 4 for this example. We are only looking at changes in temperature at this point. We know our chemical energy is not going to change, so we're going to leave that at 1 block, initial and final. So then what we really need to figure out here is T final. So if we've got a change in temperature, we're definitely using Q equals M times C times delta T. And we know delta T is the same as T final minus T initial. I know how much heat is being released, 641 kilojoules. And I know that all of these heat capacities are in units of joules per gram degree Celsius. So I actually need to convert those kilojoules into joules before I can move on. I know that there are 1,000 joules in 1 kilojoule. So to make my math nice and easy, I'm going to multiply by 1,000 and just add on the 3 zeros here. Now all of a sudden I have my joules. So that's the heat that's being released. The mass of my substance, 3.5 kilograms. Again, I need grams. 3.5 kilograms, there is 1 kilogram for every 1,000 grams. So to make this into grams, I also want to multiply by 1,000. That's allowing me to move my decimal place over 3 places. So my mass is 3,500 grams times my specific heat capacity. We want to be careful to use gaseous water because it's telling us that we have steam, which is water vapor, also known as gas. So we're going to use 2.2 joules for every gram times degrees Celsius. And then we don't know our final temperature. We do know our initial temperature of 200 degrees Celsius. In order to make the math a little bit easier on us, what we can do is simplify the equation to be 641,000 joules equals 3,500 grams times 2.2 joules per gram degree Celsius. And instead of having to deal with this order of operations, we can just call this delta T and solve for that first, because we know delta T is equal to T final minus T initial. So we can solve that later. To get delta T by itself, we want to divide on both sides by 3,500 grams times 2.2 joules per gram degree Celsius. This for us is it gets delta T by itself, and we can simplify this whole thing up here and set it equal to delta T. When you correctly divide that value by 3,500 times 2.2, we end up with the change in temperature being 83 degrees Celsius. We know that that change in temperature being 83 less than what we started because we're showing a decrease in temperature from the beginning to the end of this situation. So we want to say 200 degrees Celsius minus that change of 83 degrees Celsius gives us a final temperature of 117 degrees Celsius. So we could even add that into our graph.